AP style free response problem 11. When reaction or this reaction A produces products B and C is second order in A. When the initial A concentration is 0.100 molar, the reaction is 20% complete in 40 minutes. A, calculate the value of the rate constant in liters per minute times mole, or inverse molarity, inverse minutes is what that is. Calculate the half-life for the reaction. And then C, a first order reaction is 40% complete at the end of 50 minutes. What is the value of the rate constant in inverse minutes? The reaction A produces B plus C is second order in A. When the initial concentration at time 0 is 0.100 molar, the reaction is 20% complete in 40 minutes. 20% complete in 40 minutes. So that means 20% of this product is gone in 40 minutes. So that means at T equals 40 minutes, let me write it over here where we have room. At T equals 40 minutes, the concentration of A remaining is 80% of 0.1 molar, which is 0.08. Oh, I missed a 0 there. 0.08 molar, because the concentration has decreased by 20%. Okay? So on your equation sheet, you can find the integrated rate law for a second order reaction, and then we can plug in these values that we are given. So I rearranged to solve for K, and then for time, I put in 40 minutes. For the concentration at time T, the concentration at 40 minutes is 0.08 molar. So 1 over 0.08 molar minus 1 over the initial concentration, which is 0.100 molar. And then we get K is equal to 0.025 minutes times 12.5 minus 10, which is 0.0625 inverse molarity, or liters per mole per minute. Okay, liters per mole minute. All right, so in part B, we're asked to determine the half-life for this reaction. So we're looking for the time when 50% has reacted, right? The time when 50% has reacted. So if I start with 0.100 molar, what is the concentration after half of it has reacted? It would be 0.050 molar, right? And so we just have to find the time when that happens. So this is the same approach we took in part A. It's just instead of solving for K, now we're solving for T. So the half-life is equal to 1 over K, which we calculated in part A, 0.0625 inverse molarity, inverse minutes, times 1 over the concentration at the half-life, which is 0.05 molar, minus 1 over the initial concentration, which is 0.1. Then from here, it's just a calculation. Just plug the numbers in, and we get a half-life of 160 minutes. And it makes sense that it would be more than, like, remember 20% reacts in 40 minutes, so it obviously has to be more than that 40 minutes. And it is. It's 160 minutes. All right, now in part C, we're going to take the same approach, but now we're talking about a first order reaction, 40% complete at the end of 50 minutes. What is the value of the rate constant K in inverse minutes? So we're going to use the integrated rate law for a first order reaction and solve for K. So this is the integrated rate law for a first order reaction. Natural log of concentration at time T minus natural log of initial concentration equals minus KT. Okay, so I just flipped the equation from left to right, moved the negative sign, and then divided both sides by t. Now, where does this natural log of 1 and natural log of 0.6 come from? So at time 0, we have 100% of our reactants. So we'll just call that 1, right? At time 50 minutes, we are told the reaction is 40% complete. So if it's 40% complete, how much is remaining? 60%. So 60% of 1 is 0.6. Okay, so that's where that comes from. So minus the natural log at time 50 minutes is 0.6, plus the natural log at time 0, which is 1, and then divided by the elapsed time, which is a total of 50 minutes. All right, so just a couple of calculations, and we get a K equal to 0.0102 inverse minutes.